So hello everyone. So today we shall see the discrete time processing of continuous time signals. Okay. So in the last lecture we discussed about the reconstruction of the signal from its samples. But today we shall see that given a continuous time system, how we can implement it as a discrete time system. So first of all, let's see the broad idea behind this discrete time processing of continuous time signals. So the basic idea is, let's say I have this some signal xc of t, which is a continuous time signal, and this is let's say some continuous time system, and we have this y of t, which is also a continuous time signal. Now, in your some previous courses, particularly in signal systems or network theory, you might have seen that given a continuous time signal and the continuous time input signal, then you can compute the output signal y of t, right, as the convolution of the impulse response of the continuous time system and thus continuous time input signal. But now we shall see that how we can process this overall system as a discrete time in the discrete time framework. So let's say, so the basic idea behind is we have this xc of t. So now we will open this block continuous time system so that we can implement it as discrete time in the discrete time framework. So given this xc of t, so first of all we shall do the continuous to discrete time conversion, which will give us the signal or the sample sequence x of n. Then we process this input signal x of n to some discrete time system, which will give the discrete time output, of course. And finally, by using the D to C converter, we compute the signal y of t. Now, so far we have discussed just one thing, that this continuous to discrete time happens at some sampling time t, and also the reconstruction happen with some sampling time t. Now, so far we have discussed that how to compute or how to discretize a continuous time signal. We have separately discussed how to reconstruct that signal. So for this we shall call it the reconstructed continuous time signal. Okay, because we have seen these two processing of the signals differently. Now we shall see, if we cascaded these three blocks, then how we can implement it in the discrete time framework. So starting with the first block, so we know that the continuous to discrete time converter produces a discrete time signal which is x of n, and we have expressed it as x of n is equal to xc of nt with some sampling time t. Okay. And this is the sequence of samples of continuous time input signal xc of t, which is the input to this overall system. Okay, another property what we had, so this is the first point. The second one, if I compute the discrete time Fourier transform of this sequence, we can see that how it is related to the continuous time Fourier transform of the continuous time signal. So the relationship what we had seen earlier is x of e to the power j omega, we can express as at 1 by t summation over k from minus infinity to infinity of the frequency domain representation of the signal xc of t, j omega t minus 2 pi k by t. Okay, so this is the relationship between the discrete time Fourier transform of this sequence xn and the continuous time Fourier transform of the continuous time signal xc of t. Now the third equation what we require is the discrete time conversion, which creates or which reconstruct a continuous time output signal. And we had seen that how we can, what is the equation behind it, that's yr of t as summation over n from minus infinity to infinity y of n, and we need to process it through a low pass filter whose impulse response we had seen is given by this one. In the frequency domain, I can express it j omega because it is a continuous uh, time Fourier transform of yr of t is equal to hr of j omega, which is the frequency response of the low pass filter, and the sequence itself, which is e to the power j omega t. Okay, and since we know that how this low pass, the ideal low pass filter looks like, so mm, so I can express it as, which is equivalent to t times y of e to the power j omega t whenever we have mod omega less than pi by t. Hmm? Because hr of j omega is uh, is non-zero within minus pi by t to pi by t with the gain t. Otherwise, it is zero. Okay, so this is whatever the three equations we had seen so far. You would notice that we have not included any property of the discrete time system. So this, all these three equations or this analysis or this broad idea is in fact applicable to any type of discrete time system lying inside in the middle of this overall block diagram. But since we are focusing on the LTI system, so we can tailor all these equations to see if we how to process a discrete time LTI system now, processing of continuous time signals. Okay, so now we will focus on the LTI system, that if we fix that the middle block inside this overall block diagram is LTI, then what happens? So if your discrete time system is LTI, then you can write y of e to the power j omega, which is the discrete time Fourier transform of y of n, is equal to h of e to the power j omega times x of e to the power j omega, where h of e to the power j omega is the frequency domain impulse response of the discrete time LTI system, and x of e to the power j omega is the DTFT of the signal x of n. Okay? So now we substitute this signal into this one. Okay? So in that, then we will get yr of j omega is equal to hr of j omega times h of e to the power j omega t by replacing omega by big omega t times x of e to the power j omega t. Okay, so now substituting this equation where we have x of e to the power j omega into this equation by replacing omega in the above equation as big omega t, which is the scaled version of the continuous time big omega. Then we will get yr of j omega as equal to hr of j omega, h of e to the power j omega t, and x of e to the power j omega t as 1 by t summation over k from minus infinity to infinity xc of j omega minus 2 pi k by t. Okay, so this is the overall representation. Now, if you have xc of j omega is equal to 0 for mod omega greater than equal to pi by t. So first of all, this is the main equation which relates all the impulse responses of the subsystem inside the overall block diagram and in terms of the input continuous time signal. Okay, so now if we have this xc of j omega is equal to 0 for mod omega greater than equal to pi by t, meaning to say it is a band limited signal, then you have hr of j omega a, which cancels the factor 1 by t, this factor. Okay, because HR of j omega is non-zero for minus pi by t to pi by t with a gain of capital T. Second, in that case we can select only the term in the above expression for k is equal to 0, right? Because otherwise it is non-zero for other case, 0 for other case. So the above expression can be simplified to as yr of j omega. If we see from the above, it would be equal to the frequency domain representation of the impulse response of the discrete time system e to the power j omega t times xc of j omega, because we are taking k is equal to 0 only, and this happens only when you have mod omega less than pi by t, otherwise it is 0. Okay, now if you have xc is band limited, which is the mandatory requirement we want so that we can reconstruct it perfectly, and it is one of the assumptions in the Nyquist sampling theorem also, and we have the sampling rate at or above the Nyquist rate, then in that case you can express yr of j omega is equal to, let me write some h effective of j omega times xc of j omega. Okay, so this is from the, I have simplified this expression to this one under these two assumptions and introduce another notation as some effective frequency response. And this effective response is where you have this h effective of j omega is equal to h of e to the power j omega t for again mod omega less than pi by t, and 0 when you have mod omega greater than equal to pi by t. Okay, so what does it imply? That the overall continuous time system, what we had seen here, the overall continuous time system is in fact equivalent to an LTI system whose effective frequency response is given by this one. Okay, we shall see some example also, but there are a couple of points to be noted for the LTI behavior of block diagram, which depends on two factors. That first, the discrete time system must be LTI. Second, input signal must be band limited. Input signal must be band limited. And the sampling rate must be high enough so that any aliased components are removed by the discrete time system in the Nyquist sampling theorem properties to avoid the aliasing. Okay, we can quickly see one example. That this example says that we have some continuous time, an ideal continuous time band limited differentiator, and we want the discrete time implementation of that ideal continuous time band limited differentiator. So first of all, so let's call it, then let's give us some name of this example, dt implementation, that is the discrete time implementation of an ideal continuous time band limited differentiator. Okay, so first of all we shall see that how an ideal continuous time differentiator system is defined. So it is well known that I can write yc of t as the derivative of the signal xc of c. So this is an ideal differentiator of a continuous time signal. Okay. So if you compute the continuous time Fourier transform of this system, the frequency response, the impulse frequency response is given by sc of g omega as j omega. Okay. Now what we want is to realize this system in the form of this block diagram, for which a mandatory requirement is that the all inputs are restricted to be band limited, because this is the one of the factors on which the LTI behavior of this block diagram depends upon. Okay. Now for processing the band limited signal, it is sufficient to define your effective frequency response j omega as j omega, which is equal to hc of j omega, again for mod omega less than pi by t, and 0 for mod omega greater than equal to pi by t. With respect to this effective frequency response, the corresponding discrete time system would be, which is h of e to the power j omega is equal to j omega by t for mod omega less than pi, and because we know that it is periodic with 2 pi. Okay, so this is the frequency response of the discrete time system, where we have replaced the big omega as omega by t. Now computing the inverse Fourier transform of this h of e to the power j omega as h of n, which we can compute by 1 upon 2 pi from minus pi to pi j omega by t times e to the power j omega n d omega. So this h of, or this integration will give you pi n. You can also try to compute by yourself also, cos pi n minus sin pi n divided by pi n square t for n lying between minus infinity to infinity. Note that we have n as an integer here, so we can equivalently define this hn as 0 when we have n is equal to 0, because this term would be 0. Okay, and for n not equal to 0, it will be given by cos pi n by nt. So let's see very quickly, when we have n is equal to 0, so you will get some sin c function of type of which the limit would be equal to, in fact, become 0 here in this case. And when you have n is not equal to 0 but still n is an integer, then this part would always be 0 and this half part would be cancelled out. So the remaining part is cos pi n upon nt. So this is the discrete time filter, in fact. So if I plug in this h of n into this block diagram here with the ideal C to D converter and D to C converter, then it is equivalent to the discrete time implementation of an ideal continuous time band limited differentiator. Okay, so in a similar way you can implement the continuous time system in the discrete time framework. There is another property which is quite interesting to see, which we call the impulse invariance. So in the above block diagram, where we see the three cascaded system inside this continuous time system, which is equivalent to an LTI system for band limited input signals. So given this block diagram, that where you have this HC of t and YC of t, and here you have the continuous time LTI system with impulse response HC of t in the time domain and capital SC of j omega in the frequency domain, and we want to implement this as the above block diagram where we saw the cascade of three block diagrams, right? So this is a mandatory requirement that SC of j omega is band limited. So it is band limited. So choosing h of e to the power j omega equivalent to HC j, where big omega is replaced by omega by t for mod omega less than pi, because it is periodic with 2 pi, with t chosen as that HC of j omega is equal to 0 for mod omega greater than equal to pi by t. Then we have H effective, the effective frequency response j omega is equal to HC of j omega. In fact, this is what we had seen in the previous example where we saw the discrete time implementation of an ideal continuous time band limited differentiator. Now to hold this equivalence between the frequency response, we should have that h of n, the impulse response of the discrete time system, equal to t times the impulse response hc at nt. So here what it implies that the impulse response of the discrete time system is a scaled sampled version of hc of t. This is the continuous time, the impulse response of the continuous time system, and this what we call the impulse invariant version of the continuous time system. So many times you can use this impulse invariance property to compute the impulse response of the discrete time system, or you can carry out the same analysis what we have done above, so that we can see that how a continuous time system can be implemented using, or how we can process a continuous time signal in the discrete time. Okay, so I think we can stop here today.